Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, and we're going to talk about LU factorization. So here, this is basically going to be a brief skim. So we're not going to take too much long, hopefully not, but we're going to skim through this section because this really isn't part of the curriculum, but we're going to go through it just a bit. So let's hope we don't reach too long. Right. So we're going to revisit the problem of finding solutions to a system of linear equations, but we're going to develop a new approach, right? So this is basically a more efficient way of finding solutions to a linear equation, okay? And so let's do an example. We're going to start immediately with an example here. So we want to find solution to a linear system. And we know three things to do this, right? We actually know a couple already, but we know how to solve the linear system using elimination, substitution. We also know how to do Gaussian elimination, right? So, okay, we have the linear system. I'm immediately going to, actually, this is the linear system. I'm just going to write that out real fast. This thing is 160. Then we have x sub 1 minus x sub 3. That one there is 20. Then we have x sub 1 minus x sub 2. This one is negative 40. Then x sub 2 minus x sub 3. That one is 60. Okay? And then so the first thing I would do is express them in its compact form, ax equals b, where A has the matrix 1, 1, 0, 1, 0, negative 1, 1. So these are the entries. And we got them from the coefficients of the linear system. What's x? Well, x is just going to be 1 to 3, which we already know. What's b? B is the constants in the right-hand side. So that's 160, 20, negative something, 40, negative 40, and then 60. Okay? So here we use a new approach to find the solutions to this system. Okay? So later we're going to see how this thing, A, we're actually going to make A into two matrices. It's going to be 1, 0, 0, 0, 1, 1, 0, 0, 1, 2, 1, 0, 0, negative 1, negative 1, 1. Okay? And that's also going to be multiplied by 1, 1, 0. Now you might be shocked at how in the world did a matrix become two things? That's going to be A. So we say that, let's say this is the matrix L, this is the matrix U. Because here we see this is a lower triangular matrix. And so we see the zeros all the way here. This is an upper triangular matrix, so we see the lower area being zeros. So we have a lower multiplied by an upper triangular matrix. That's what makes up A. Okay. And so this is actually LU. That's the LU factorization. So AX could be written as LUX, and that whole thing is B, which looks more complicated, but actually allows us to break the problem into two systems, right? So we say So here we break the problem to do systems. And so we let y vector be ux. And so when we replace this ux by y, we get lyb. So we actually broke it down. Now you might be wondering, why not just do it directly like this? Why make it complicated and solve two things? Well, for one, solving a matrix that's upper triangular or lower triangular is actually easier than solving a regular matrix. That's why. Okay. And so this one is actually easy. When we say, let's try this first one. Okay. So the first one is saying the upper matrix U. So it's going to be 1, 0, 0, 0, 1, 1, 0, 0, 1, 2, 1, 0. Then lastly, 0, negative 1, negative 1, 1. So that thing multiplied by y1, y2, y3, y4 is equal to b. Oh, this is a lower triangular matrix. 160, 20, negative 40. I hope I'm not running out of time. And then 60 again. Well, this is quick, right? So we just do, here in this case, we do a forward substitution. Y sub 1 is 60. Y sub 1 plus Y sub 2 is 20. So here, it's really nice to see it this way. Y sub 1 plus, so this is what we call forward substitution. And we can do the same thing with the other one, which we already know as back substitution. So we get this nice linear system. I think that was a 4, right? Yeah. And there we have it. Cool. So we actually have a solution for all of these guys. So we just use our usual back substitution method, and then we get. And then we can also do the same. Here I think we can all figure this one out, but we basically do everything for y ux. Okay, you can figure all of that out. And so the idea is that decomposing the matrix A into LU, so we actually call it LU decomposition. It actually makes it easier to find the solution, but we do not know these two, L and U. And so the problem now is, how do we find L and U? Okay. And so actually the number of computations required to find L and U from A, then perform the two back substitutions, is about the same as simply reducing A to echelon form. Therefore, for a single system AX equals B, there is no benefit to finding L and U first. However, some applications require the solutions to many systems that all have the same coefficient matrix. So there are some instances where we have to find L and U. Okay. So here's how we find L and U. And this is not too important, but it helps when we do this. Pretty sure I talked about this in scientific computing, but it's a really, really similar concept. So when we find L and U, so here we look at the buzzword LU factorization. So we say that if A is LU, U is an echelon form, L is lower triangle, or it's a lower triangular matrix. U is an upper triangular matrix. Oh, it says with ones on the diagonal, making L unit lower triangular. Then the product is called an LU factorization of A. So this is what that looks like. Zeros on top, non-zero entries at the bottom. Well, there's a zero here, but most of it is not. And we say here that U is always in echelon form. So this U matrix is always in echelon form. So we say that, yes, this is the LU factorization of A. And so we're going to do an example of finding L and U. So find LU factorization of A. So how do we do this? So say my A is negative 3, 1, 2, 6, 2, negative 5, 9, 5, 6, negative 6. One thing I would do is just program this. Okay, so here's how we're going to do it. Turning A to echelon form gives U. Okay? We build up L one column at a time as we transform A. Okay? There are some steps to do this. But to get, so I think the problem is getting L. Okay? And so let me think. So let's start off with this matrix, right? Now, get L, the L matrix. The idea is we build up one column at a time. So we do one column at a time. And we do this as we transform A through a sequence of row operations. Okay, so we're gonna say, let's try this out. So we have A as this with these entries. Okay, that's A. That's equivalent to 1, negative 2, negative 3, dot, 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 dot. How do we do that? Well, yeah, where do we get 1, negative 2, and 3? Huh. What we did was, okay, we take the first column of A, divide everything by 3, and that would be the first column of L, right? So what we did was, we looked at this, divide by 3, and that column is in L, okay? Then I keep going. That means we don't know yet. And then we perform row operations as usual. Okay. So this thing is going to be L. Is this L? I feel like I should have done it here. Or right about there. Okay. Right. So we do row operations here. We're somehow going to get negative 3. Whoops. One, two. 041, or -1, 080, right? And then we take the second column of this. So we say this is A sub 1. We take second column of A sub 1. So we're actually going to take this one. And what are we going to do with that? We're starting from the pivot entry 4 down. So the entries are shown in boldface. And divide each entry by the pivot. And so what that's going to do is, so once you somehow made this 0, we want to look at second pivot. So in this case, 4, and divide each entry by the pivot. Okay, so we actually divide this thing by a 4, divide this thing by a 4. And so that's going to look like, for our L, it's going to be 1. So we keep these. And then here we put a 1 and a 2. And we still have these on bar. And then we keep going. We need that last entry. So again, we perform row operations on A. So we do A sub 1 being this guy. 1, 4, 8, 2, -1, 0. Now this thing is going to be equivalent to -3, 1, 2. Now you have it in echelon form. Okay. Now this thing is A2. This right here is a negative. So now that the original matrix is in echelon form, it is upper triangular. And the two small items remain. Okay. First, we set U equal to A2. This thing is equal to U. That's the U matrix. But then how do we get the L matrix? We finish filling up L. Since L must be unit lower triangular, we add a 1 in the lower right corner. Oh, does it say L has to be unit lower triangular? Oh, with 1's on the diagonal. Huh. So this thing is going to have a 1, even right here. Oh, it's going to have a pivot of 1's. Okay. So we're saying here that, we have, or since L is lower, or unit lower, oh, it's always unit lower triangular. Then add a 1 in lower right corner. How do we do that? We're going to add a 1 here. So L is just going to be 1, -2, -3, 1, 2, 1. And the rest is 0. So that's our L. Then our U is this guy. How do we check if this is correct? Well, when we multiply these two, we have to get this A right here. Now, a computer can do this on their own, right? And there we have it. Okay. So not all, okay, here's the thing. Not all matrices have an LU factorization. There's a theorem that gives a condition that will ensure such a factorization exists. Okay. I kind of don't want to go through this, but it's okay. 147. Actually, I'm close. So let's immediately up through the theorem here. I wonder how much time I did. Probably an hour. So we say A is an n by m, and it can be transformed to echelon form. So say we do that without interchanging rows. Huh. We can interchange rows. Let me. Ooh. When we don't change the rows, there exists a unit lower triangular matrix L. L in L is a square matrix n by n. This is unit lower triangular matrix. And then n by n echelon matrix U. Let's complete that. It's okay. Such that A is just LU. Okay? Right. Note that if U is a square matrix, it is an echelon matrix, and it's also upper triangular. And later in this section, we explain why the algorithm for finding an LU factorization works and justify using the theorem that we just stated. Okay, there are some examples of finding LUs, which I'm going to skip because we don't need to know that. But the idea for a lower triangular matrix is all of the things have to be a 1. Okay? Okay, let's do an LDU factorization, which I think is also shouldn't be that hard. LDU factorization is a variant of LU, right? So we say this matrix A is going to be LDU. So we say where L is lower triangular, that is a matrix. U is upper, and it's an echelon form. But then D is a diagonal matrix. And so to find the LDU, we follow the same procedure in finding LU. And then the end form D and modify U. Okay? So LDU. Let's do an example. What example was I in? Like 2? Okay, let's do 3. So we want to find the LDU factorization for this given A matrix. 2, 8, 0, 4, 18, -4. Then we have -2, -2. Then we have -13, And we start by finding an LU, right? So again, we look at the three rows. And so, okay, I'm just gonna put my L somewhere here. When I look at these three rows, I immediately divide all of them by 2. So I do 1, 2, -1. I have a dot here. Okay. And now we perform elementary row. 0, 0, 2, 6, -4, 13, -13. And then we again update the L. So now we look at 2 and 6. We divide both by 2, so we're gonna get 1, 3. Okay. And then we keep going until we get to an upper triangular matrix. So we're gonna get 2, 8, 0. And I think we're done here. 0 to -4. And then we get 0, 0, -1. And then now here we have a -1. Or in this case, actually, we could just scale the whole thing. This one I could just divide it, so I would just get my L to be 1. And so now we actually have this is U, and then this is L. So we can note that our D, we're just actually taking these two things. Actually, this we're just getting the diagonal. Right? And then now we can modify the new U. This will all divide by, or this will all become 1. How? Because we just divide every row by 2. So here I get 1, 4, 0. Divide this 0, 0, 0. Divide this by 2, I get 1, -2. Divide this by 2. Actually, multiply this by -1. I just get 1. That's the new upper. And so we say that the old U is just the new U multiplied by D. That's how we find LDU. Now, why does it work? In our examples, a central part of the LU factorization algorithm is using elementary row operations to reduce the original matrix to echelon form. Right? So when we somehow manage to reduce it to echelon form, that's going to be our upper matrix. Oh, there is a proof here. Jeez. Okay, I'm not going through that proof. But the idea is to just make it. So in scientific computing, we did talk about this. It's regarding to computational complexity. And the idea behind that is when we decompose matrices and we do some arithmetic with them, then decomposing them actually makes it faster to compute. So we're talking about how fast things compute in scientific computing. And if we decompose some matrix into its, I don't know, we have LU decomposition, we have singular value decomposition, SVD, we have QR, we have tons of ways to decompose, but the idea is to make it faster, right? And so that's what we're doing here. We're just trying to make everything faster. Anyways, so that was it, pretty short for section 3.4. And we're also going to make this other one short. It's Markov processes, but I'm going to do that in the next video. So I'll see you there, guys.